All right, let's go ahead and start chapter 11 unless you have any questions on chapter 10 stuff. And there's example problems on the worksheet. Definitely go over those. The answer key is online. But I kind of want to make sure we get everything done by Thursday so that we can have time to do your exam and feel good about it. Okay. So let's talk about nuclear chemistry. So far, when we deal with chemical reactions, what part of the atom changes in a chemical reaction?
None of it.
I didn't say what part of the nucleus. What part of the atom changes during a chemical reaction? The electrons, the outside, right? Okay. In a nuclear reaction, it's the nucleus that changes. Okay? Hence, it's called nuclear reaction, nuclear chemistry. It's actually called nuclear physics, but we're going to call it chemistry so it doesn't scare anybody away. Okay? Well, maybe it still scares away, I'm not sure.
Chemistry is physics at like a really small scale.
Yep, that's what it is. Okay, so the nucleus, we know what the nucleus is, right? That's where, what lives in the nucleus? Protons and neutrons, and the total charge is positive, right? And the particles of a neutron are called nucleons. Particles of nucleus. So
why would they not be called protons and neutrons?
they are.
But when they're together, they're nucleons?
No. We just have another name for the particles of a nucleus. Just another word you guys have to get down, right? Sorry. These are protons and neutrons. Is that the only particles of the nucleus? No. But that's all but that's all we're concerned with. Okay? So you ever heard of quarks and antiquarks and muons, neutrinos?
Yeah.
We're not going to cover all that stuff. That's nuclear particle physics. That was a great class, by the way. But we're not going to do that in here. Okay? But we are going to talk about there will be some weird stuff going on in this chapter. Like, what? There's an electron in the nucleus? Yeah, we'll get there. Okay. Anyway, so we give it a different name. All right. So elements have several different naturally occurring isotopes. You guys remember what isotopes are? Who can tell me what an isotope is?
It's an atom with a different
Atomic mass.
Yeah.
Different number of neutrons, same number of protons. Do you remember that? So we can have carbon 14, for example, and carbon 12. Two different isotopes of carbon. They both are carbon because they both have 6 protons, but they have different masses because they have different number of neutrons. You with me? So how many neutrons does a carbon 14 isotope have? 8 neutrons and 6 protons. You add them together and we get the 14. Is this kind of coming back to us from the first exam? Okay. And carbon 12 has 6 neutrons and 6 protons. You add them together and you get 12. So this is just a quick review of what we already learned. Yeah? All right. Now, some isotopes are stable. Here's our stable isotope. And some are unstable. So carbon 14 is unstable. The majority of carbon is what isotope? carbon-12. How do we know?
Who's stable?
Sure. And the molar mass of carbon, so the atomic mass of carbon is 12.01. Really, really close to 12. Why is it not exactly 12? Because there's other stuff, right? There's other isotopes. You remember this, guys? Okay. So for this exam, I'm not going to have you calculate the atomic mass. We already did that. So here's a new term, radioisotope. A radioisotope is an unstable or radioactive isotope. Yeah, unstable or radioactive isotope. Radioactive means it's going to decay, it's going to break down. Why does it do this? So that it can become more stable, okay? And it's going to do it whether we do anything about it or not. So in a chemical reaction, what can we do to increase the rate of reaction? You heat it up. You increase the pressure. You increase the concentration. All these things, we can speed up the reaction, or we can add a catalyst, right? Right? But for a nuclear reaction, we can't do anything to change the rate, as far as we know today. Okay? So I wonder how many times I lie, because we don't know everything about everything, or we don't know everything about anything really. So this is just what we know today. What I know today, I guess, because there's probably things that we know that I don't know still. You guys understand that, right? I'm not this. Okay, all right. So isotopes of an element will react the same way. So if we have radioisotopes of elements, so carbon-14 is going to react the same way as carbon-12 does. And it's going to react whether it's a single element or if it's in a compound, like in methane or something, okay? And it just kind of behaves the same way chemically. But nuclearly, it's different. But there is one note to make. Heavier isotopes react slower.
Is that why, like, in Oppenheimer, they're talking about, like, a heavy hydrogen bomb? Because you have, like,
Yeah.
a longer reaction?
I don't know about, probably. But heavy means it's going to have, like, tritium or deuterium in it.
Okay.
A heavier hydrogen. Yeah.
So it's not like a pure hydrogen, whatever, that they were talking about.
Yeah, it's not going to be only deuterium or tritium, but so there's heavy hydrogen in the ocean, in the water in the ocean. Deuterium, that's where we find deuterium. But in this chapter, we're not going to talk a lot about chemical reactions. Okay, so that's basically all I'm talking about, chemical reactions, kind of how they're different than nuclear reactions. So let's make a few notes of nuclear reactions. So obviously, they involve the nucleus of the atom, hence the name. So remember when we talked about the atomic theory, John Dalton says atoms cannot be divided. Can they? Yes, they can. But he did say that they're not destructible. Whatever we have now is whatever we're going to have. So we can't destroy them, but you can divide them. And then different isotopes react differently. When I say react, I mean nuclear reaction. So chemical reactions, they react the same. Nuclear reactions, they react differently. So different isotopes of the same element react, I should put nuclearly react differently. So for example, you have carbon-12 and you have carbon-14. Carbon-12 is not going to react nuclearly, but carbon-14 is unstable, so it's going to.
What is these two at the top? Is it different isotopes?
Different isotopes react differently. Yep. And kind of like we mentioned before, the rate of the nuclear reactions are independent and unchanged reaction. That's the, you ever see me write that? And they're unchanged by temperature we talked about, pressure, or a catalyst. We just cannot speed them up. We can't slow them down. They're doing what they're doing. They're doing it right now in the Earth, and that's why the center of the Earth is warmer than up here, because there's nuclear reactions going on. They're decaying. And that's why the sun is hot. Okay? And the stars.
Is it process or pressure?
Pressure. Pressure. Okay?
And the sun is a fusion reaction, right?
Catalyst.
What's that?
The sun is a fusion reaction?
Yes, and we'll get to that. So we talked about this also. The nucleus will decay in element form or in compound form. For example,
Well, decay in element or compound?
decay in elements. So if we had carbon-14, it would decay. But if there was carbon-14 and carbon dioxide, it would still decay. Does that make sense to everybody? So I'm basically just writing all this stuff down that we kind of already just talked about. And the big thing, energy in a nuclear reaction is much, much greater. There that is again, right? Much, much greater than in chemical reactions. So we get exothermic reactions in a chemical reaction, but the exothermic in a nuclear reaction is much, much more energy, more heat produced. Good? Any questions on the difference between nuclear and chemical reactions? Okay. So let's talk about the types, and then we'll dive a little bit deeper into each type. Slow down. Okay, so we have decay or emission reactions. And the different ones are we have alpha emission. And we'll go into each one of these a little bit deeper. Beta emission. Why do we call them alpha and beta? First two letters of the Greek alphabet. Okay? And positron emission. What the heck is a positron? We'll get there. And then the other type of nuclear reaction we're going to talk about is energy created reactions.
Position emission.
Positron emission.
Positron.
And the different energy created reactions are going to be electron capture. Actually, electron capture is not an emission. We're going to just throw down this energy created. They all create energy, but the two of them create the most energy are fission and fusion, we'll get to. So electron capture, nuclear fission, and nuclear fusion. Okay, there's the list of the 6 different reactions we're gonna discuss. But before we do, let's talk about the different particles. We just learned a new one, positron. And alpha, beta, yeah, those are different particles. Let's, I'm going to draw a table that just describes these different particles. And we have symbols for them, just like we learned the different symbols of an atom, right? We're going to do the same thing with nuclear reactions. We good? All right, so particle. We got the mass, the charge, the symbol, and the description. Okay, the first one we're going to talk about is an alpha particle. Alpha particle has a mass of 4, and its total charge is +2, and its symbol is 4-2He. Does that look familiar? What is that? It's helium. It's not a helium atom. It's the nucleus of a helium atom. So it has 2 protons, therefore a +2 charge. So basically, this bottom number represents the charge. Good? And the top number represents the mass. We kind of already knew that. Okay, another particle is a beta particle. Beta particle basically doesn't have any mass. It really does, but these are all relative masses, right? And the charge is -1. What is a beta particle? It's an electron, but it comes from the nucleus. Did you guys know protons aren't just solid masses? Neutrons aren't just solid masses. They're made of other particles. We're not gonna dive deep and say what all particles they're made of. We're gonna just keep it simple. So these are electrons from the nucleus. A little bit different than just regular electrons. And then a positron. Am I going too fast, too slow?
Yeah.
Positron also has a mass of 0. Its charge is +1. What is it? It's a positively charged electron. Boy, I guess I should say what? Hence the name positron, right? Right? So it's just a little guy. What?
Is that
Oh.
like when it changes and gets attracted to other
Well,
whatevers?
It pops out of a proton, and the proton becomes a neutron. We'll get there.
They're just immaculately concept.
Well, it has to, so an unstable isotope has to become stable somehow. We'll talk about this. We'll get there. Right now, I'm just giving you the particles.
Is it one? Like, it's one?
Yeah, this is a positive one.
Oh,
Is that what you're talking about?
positive one.
So it's a 1 there. Since there's not a negative, it means it's positive, right? And then the last one we're going to talk about is a gamma ray. You guys know what gamma rays do?
It's not like what X-rays are.
No, X-rays are lower energy, but they're the same. It's basically light. But what a gamma ray does is, if you guys get gamma radiation, it turns your skin green and your pants purple. So be careful, right? I'm just teasing. Sorry. Okay. But that's what gamma is. It's the same stuff. Gamma radiation. It's what it is high energy light. Highest energy.
Hold on. No.
Now, when I say light, I'm talking about electromagnetic radiation. So just like visible light, it's just electromagnetic radiation. But it's right smack in the middle of our scale. We have radio on the lower side, and we have gamma on the higher side. We have microwave, we have infrared, we have X-ray and ultraviolet rays. All of those are classified as light. Why do we call them light? Because they all travel the speed of light. Okay? That's really what it is, just high energy light.
Mass and charge.
Well, what's the mass of light? 0. What's the charge of light? 0. It's all 0.
So we're not talking about photons.
It's a high energy photon of light, yeah. But it's not, well, no, it's not a photon. Photon is visible light. This is invisible light. Well, most light is invisible,
Right. Yeah.
right? Yeah.
What is that symbol? Is it a 0?
This one right here,
Yeah.
it's a gamma. A Greek letter gamma. We have alpha, beta, gamma. Makes sense, right? All right.
Okay, wait. Are you gonna tell me that there are like CBE rays also, but we're just not worried about them?
No, we're gonna. This is it. This is it.
Okay.
That's it. That's all the particles. Are we good? Really, this is the easiest chapter. Now, it sounds a little goofy, but these are just the names of the particles, guys. I didn't just show you anything yet. Okay? But what I am going to show you, you guys are going to like. I think. I hope. Because it's simple. Okay, here we go.
Simple is relative.
It sure is. That's why I say I hope. Okay. So let's talk about alpha emission. Sometimes we call alpha decay. Decay, when something decays, things are being emitted, right? So you might see it either way. And what happens here, so we have 4,2-HE, and what is it? It consists,
Are we using helium as an example, or is helium?
no, that is the it's not helium,
Oh,
it's the helium nucleus, just the nucleus.
Okay.
And it is one particle We know its charge is +2, and we know its mass is 4. Therefore, +2 because it has 2 protons. It must be helium, right? Okay? But it's just the nucleus. There's no electrons buzzing around it. Okay? So it consists of 2 protons and 2 neutrons. So an atom is going to undergo alpha decay or alpha emission when it just has too many protons and too many neutrons. If you look at the periodic table, then we see that, so if for oxygen, for example, most oxygen is 16 and it has 8. How many protons and how many neutrons? 8 and 8. That's a 1-to-1 ratio of neutrons to protons. You with me? If we look at calcium, what's its mass number? About 40? And it has 20? What's its ratio of neutrons to protons? 1-to-1 ratio. It turns out a 1-to-1 ratio or close to a 1-to-1 ratio makes it a stable isotope. Okay, and you don't need to know that so much. I'm just telling you to kind of help you to understand. Well, if we have, for example, if we have carbon-14, this ratio is 8-to-6. Tells us it's unstable. So what's it going to do? It's going to do something to get closer to that 1-to-1 ratio. And does it have to be exactly 1-to-1? No, but really close. Okay? As it gets heavier, the ratio is going to be a little bit bigger than a 1-to-1 ratio. Why? Because what are neutrons doing?
Neutralizing the positive charge of the protons, all the protons. You have some
Not
proton
quite.
mass.
It's the electrons that neutralize the charge, right? What are the neutrons doing? They are holding the protons together. Now why? Think about what the protons are positive and positive. If these guys come together, what happens? They would repel. But where are they? They're so close together in that nucleus. And how are they held together? By the nuclear strong force, which is the strongest force that we know of so far. Okay? And those neutrons act as nuclear glue. So as we get more and more protons, what happens to the number of neutrons? Let's say we take uranium. How many neutrons does that have? Like 147. My math might be off. To 92, right? We got to have a lot more neutrons to hold that number of protons together. Does that make sense? And so as it gets heavier, we have to have more neutrons to make it stable. So that ratio is going to be a little bit greater than a 1-to-1 ratio as it gets heavier. But as it gets heavier, there also becomes more unstable isotopes. Does that make sense? Because they're just buzzing around in there trying to break apart. Those neutrons are trying to hold them together. Make sense so far? All right, let's do an example. Of alpha emission. So uranium-238 is going to emit. That means one of the products is going to be an alpha particle. Does that make sense in your mind? So it's not a reactant. So it's sitting here by itself, and it just shoots out one of these alpha particles.
Which is not helium,
It's a helium nucleus.
Okay.
Why does it? Because it has 2 protons, and that's what tells us, by definition, what helium is.
And so this helium is just immaculately concepting itself from
Yeah,
your.
not immaculately, but it's popping out of the nucleus of an unstable isotope. And why does it do it? Well, because it has too many protons and too many neutrons.
So it's just
Wanna
making
get
up
rid of
helium.
it?
No, it's not making it up.
I'm gonna stop.
It's not creating it. What is helium made of? 2 protons And most of helium is 2 neutrons, right? So if it pops out a particle that has 2 protons and 2 neutrons, it is helium.
So the helium exists in uranium form.
No, helium has electrons around it. But the helium nucleus, yes. Okay? Well, if we get rid of a helium nucleus or an alpha particle, well, is it going to still have a mass of 238? No, it got rid of 4, so what does it have a mass of? 234. And you guys can calculate this, right? This is the calculations that you're going to do in this unit.
So just simple subtraction.
Simple, yeah. Well, okay. And if we start with a positive 92 and we get rid of two protons, what are we left with? Does anybody know what isotope that is? Oh, yeah, you got it. I love that. Okay. So that makes thorium-234. Now, this could still be unstable, right? Now it might undergo a different radioactive decay until it's going to keep doing that until it becomes stable. Does that make sense? Yeah.
So that would be an isotope of thorium?
Uh-huh.
It's real, or
Yeah, all isotopes won't have a mass of 234.
because 232 is the actual.
Yeah, you're going to have different isotopes. Yep. So
So
does that mean this thorium is not stable, right? Because it's further from the average.
Dude, are you gonna tell me it's just like helium all the way down? Cause like this uranium gives up helium and becomes thorium, and then that gives up a helium and like becomes something else.
It might not give up helium. It might give up a beta particle.
Okay.
So for your guys' case, you don't have to know what it gives up. It's going to be told to you. But you do have to know, if it tells you if an alpha particle is emitted, you have to know that it's helium.
Okay.
And if a beta particle is emitted, you have to know it's an electron. And if a positron is emitted, you have to know it's a positive electron. You with me? Okay. Should we do one more? This time I'm gonna use algebra to figure it out. In fact, let's do that right now with this one. So I have a mass of 238, and the law of conservation of matter and energy says whatever mass I have to begin with, that's what I have to end with, right? So this arrow, that's like my equal sign, and I have 4 there. Then I could say plus x. I can figure out what x is, right? I subtract 4 to both sides. Oh, x is equal to 234. That's how I know what that mass number is of my new isotope. You with me? And I can do the same thing with this bottom number. I have a positive 92 or 92 protons, and I get rid of 2, or I have 2 in the alpha particle, plus a y I could call it, and that's going to be 90, and that's where I get this number. How did you get this, Krista?
I know the numbers.
Oh, because the atomic number of thorium is 90. I'll look on the periodic table, find 90 on the periodic table. Oh, and that tells me thorium. Does that make sense to everybody? Okay, should we do them on our own, or do one more just for practice? Together. Okay, here we go. So let's do polonium-208. And polonium is 84. She could have told me that. And we're going to undergo alpha decay again. So what's the product? 4,2-He. It's not always going to be that. If it tells us it's alpha, it's going to be alpha, right?
Or 82 lead, which is PD.
So what's our new mass? 2. Our mass is the top number, 204. And what's my atomic number? 82, and that tells us it's lead. Can you guys do this? And do you like the math equation better? Okay, then use it. And when we do beta, most people make the mistakes on beta. This is pretty straightforward, but beta, we have to deal with a negative number. And that's where we make mistakes. So here's a way to check it, guys. 82 plus 2. Does that equal 84? Then we did it right. 204 plus 4. Does that equal 208?
Yes.
Then we did it right. And then just double check to make sure number 82 is lead, right? Not too bad. Is that too bad? What do you think? Pretty straightforward? Okay, ready for beta? Okay, beta emission. Let's do carbon-14 generally undergoes beta decay. Since it's a decay, that means we're going to get rid of a beta particle. What's a, yeah?
So for the last example, we get 2,4, like the lead mass is says 207. This doesn't affect something like.
No, that just means it's a different isotope. Yep. So never look at the periodic table to determine what the mass of our isotope is that's going to be left. We've got to do the math. Okay? Great question. So what's the particle that it's emitted if it undergoes beta emission?
A negatively charged electron.
Yeah, just an electron. And that's the isotope symbol for an electron. And what are we left with? If we the mass is 0, so if we get rid of 0 mass, what are we left with in mass? 14. We started with 14, we got rid of 0, we end with 14. What if we start with 6 protons and we get rid of a -1 charge? Positive 6 gets rid of a -1. What's 6 minus a -1? And that's where most people make mistakes. They will say 5. Most people that make a mistake on here, that's what they will do. Now, if we write the equation out, let's say we're looking for X, Y, and Z, right? We're looking for this unknown isotope. Write the equation. 14. This is like the equal sign. 0 plus X. So 0 plus what number is 14? 14. So that means we're going to have a 14 up here. And then we do the bottom number, 6, equals the bottom number here is -1 plus Y. How do we solve for Y? We add 1 to both sides. You with me? And it gives us 7. And so what, besides Krista, what element has an atomic number 7? Nitrogen. I'm not going to say that anymore. You can tell me. Okay. I just want to make sure we all got this. Okay. So that's our leftover isotope. What's bigger? Has the same mass, but it has, is it stable now? How do we know? Because it's a 1-to-1 ratio. You with me? And that's why if it underwent alpha decay, would it become stable? No. That's why carbon-14 doesn't undergo alpha decay. You don't have to know which one it's going to undergo. That's more nuclear physics where you'd have to know that. Okay? But we're going to keep it simple. I'm just going to say carbon-14 undergoes beta decay. What's the remaining isotope? You want to do one more? We have iodine 131 undergoes beta decay, so it's just still going to be get rid of an electron. In fact, let me tell you, let me show you what happens in just a minute. So what are we left with? What's the mass that we're left with? Everybody.
131.
131. Does everybody get that? We start with 131. We get rid of 0. We end with 131. We start with positive 53 on our charge. We get rid of a -1 charge, so that means we have 54. And check it before you're done. 54 plus -1, what does that equal? Okay, it works out. Always check it. People make most mistakes on the beta decay. Okay, make sure we got that. And so what is it? Xenon? We good? Here's what's going on. We have a neutron. Neutron has a mass of 1, charge of 0. It gets rid of a beta particle and turns into what? A proton. So our ratio needs to be, our neutron to proton ratio needs to be close to 1, right? If we have too many neutrons, then beta decay will happen
Create more protons.
to create more protons, and that's exactly what it did here, right? It turns into a different element, but now it's stable. Does that make sense to everybody?
Okay, so the neutron that you're talking about, it's decomposing to yield that proton, but also an electron?
So the neutrons and the protons are made of other particles. We're not going to talk about what all particles. So so if I draw it here, there's a neutron here, and an electron pops out of the nucleus, now making the nucleus positively charged. Has the same mass because it didn't lose any mass, right?
And this is a non-immaculately concepted electron,
No, it's there. It's there.
just not electroning until it decides to electron.
Sure.
Like, is that how it works?
Yeah.
It's
I told you it's going to mess with your head a little bit, but it's really not that complex, right? The math is pretty straightforward.
So, like, hypothetically, in the example we did where the carbon-14 becomes nitrogen, a nitrogen could be a carbon-14, just hasn't.
Not anymore, it can't.
Well, okay, so all carbon-14s are nitrogens until proven otherwise?
Well, here's what happens. So that probably is it, guys, and we'll finish this next time. But let me just draw this here. So if we have 1, 2, 3, 4, 5, 6 protons. 1, 2, 3, 4, 5, 6, 7, 8 neutrons holding it together. Now what happens is maybe in this one right here, an electron pops off. And all it does is turns that neutron into a proton. And since it has more protons now, it has to be a different element. But in our mind, we draw these neutrons and protons as small spheres of mass. But it's not. They're made of several different types of particles.
So, like, everything is cake until it's not cake?
That's right. Exactly. All right, ladies and gents, have a fantastic rest of your day.